Okay, hi. So I'm back. Yeah, so I just wanted I did another one in R2 just to have another example for you. So if I just continue with the real estate and I just added two more predictors to it. One was a variable GAR, which was the number of cars that could be parked inside the garage. So this ranged from 0, no garage, up to something like 6 or 7. And lot, which was also in square feet. And I type LM with the variable names, and I get this new little b0 and b1, etc. So I found that lot, apparently a square foot in the lot only increases the price along the fitted hyperplane by about $1. Sounds like a good deal, but more on this in a second. The building, roughly the same, right? It comes down a little, but that's because there are these other predictors in here. And remember, this is just trying to attain fit mathematically. The other one, garage, looks quite important here. Bigger garage implies maybe bigger house, other good things. The AC came down a little, but still looks important. Again, I have to caution you a couple things. The way to read this is that the fitted line behaves this way, not that the actual system behaves this way. This, we still need to make inferences and to understand better what the betas are. This is for the B's, and this is the fitted hyperplane. This is the linear fit. But certainly it's related to the betas, and we'd like to have an intuitive way to understand it. There is more coming in the chapter on multicollinearity about this too. When the predictors are correlated amongst themselves, it's the coefficients are not really independent. So it's not saying that that each predictor has its importance is directly proportional to its coefficient. That's not true. So if they're all completely uncorrelated, it is true, but that's very rare usually. So in this case, it's not true. They're fairly highly correlated. So we can't really read it that way. All right, so more on that to come in this juicy chapter 7. So a lot more. Okay, let's see. So plan, what to do. So solution. So we're going to standardize. So we have to introduce some new definitions and things like this. So one approach to 1 and 2 above, by this I mean the numerical effects and the comparability, is to standardize all variables, the response and the predictors. You have to do it the same way, otherwise you'll distort the system. Okay, so there's two standardizations you need to know, and there are more than two, but there's two main ones you need to know. There's one that's the default for standardizing vectors in statistics, and then the other one that's used when you're doing multiple linear regression, which is based on the first one. So we just have to do this. So all right, so the first one is, so when we say we standardize a vector, so standardizing a vector, such a long word, how should I, standardizing a vector means to subtract its mean, and we mean sample mean, of course. We don't know what the hell these things really are. It's sample mean, and divide this after we subtract by its, sample standard deviation. Yeah, right. So the standardization is I send y to y minus y bar. This means every element is y bar in this vector. And I divide by its standard deviation, which is a scalar. So sy, I'll write sy, I'll say what it is. This is the sample variance, the square root of the sample variance. Okay, so this is just 1 over n minus 1. So if the vector has size n, sum 1 to n yi minus y bar squared. Here it's a vector. This means vector where each one's y bar, right? All y bars of y bar. Okay. Okay. This means just scalar. Okay. Yep. Okay, so also for each predictor variable, we'll use the standardization, say xk is the vector xk minus, we'll write it like this, xk bar. Again, everything is analogous up here, but this is a little different. We won't write s of xk, that's a little redundant, so we just write sk. And you should know that that means this. Yeah? Okay. All right, looks good. Okay. Okay, so these are called standardized vectors, common in statistics. All right. With these standardizations, then, a 1 unit increase in the standardized variable is analogous to a 1 standard deviation increase in the original variable. So let's write it down. So under these transformations, some things you have to write out, comma, a 1 unit increase corresponds to a 1 SD increase in the original variable. We should be able to see that. If we take y minus y over sy and we give it a 1 unit increase, well, this is, if this goes here, this is true if and only if y y goes to y plus sy. Okay, so I don't want you to get confused here, and I think I'm being a little confusing. I'm not saying we're changing the actual vector y, but if I look along values of y under this transformation, where now I look at y bar and sy as constants, then this is true. Okay, so sorry if this is confusing. Note y bar, I wrote not, maybe that was Freudian. Y bar and sy are fixed now, so they're not changing. Okay, So for MLR, there's one more, and this is the one we really need to, well, let's do an example first to practice example. So say find the standardized vector for, say I have y equals, say 0, 4, 4, 1, I don't know, say 5. Let's go 6. Okay, there we go. All right, give you a second. Y bar is 3, right? So y minus y bar is equal to minus 3, 1, 1, minus 2, and 3. First thing you should notice is that they add to 0. Okay, the elements add to 0. Now I need sy. So sy is just equal to the square root, right, of 1 over n minus 1, so I have 1/4. And now I'm just going to square these, right? So I have 9 plus 1 plus 1 plus 4 plus 9. And this is 10, 11, 15, 24 over 4, so that's 6. So I get the square root of 6. So you see you get y minus y bar over sy equals minus 3, 1, 1, minus 2, 3 times 1 over square root 6.